And in addition to my academic work, I'm also working as a researcher student at Lightricks under the data science group of ASI. And now I'm working in a research related to LTX Studio. Okay, so in our last session, we had a fine-tuning overview lecture in which we talked what is fine-tuning and how to fine-tune your LLM. And we also emphasized the main differences between fine-tuning, RAG, and prompt engineering, and in which scenario we want to use each one of the approaches. Then we had the fine-tuning code example in which we fine-tuned the medical diagnosis model. So you have seen all of the different phases in fine-tuning from data preparation to training. And we finished the talk with the challenging topic of how to evaluate an LLM. So in today's session, we will talk about a real use case from Lightricks that successfully deployed in VideoLeap. And also this work has led to a research paper that has been submitted to EMNLP 2024 conference. Okay, so this is the paper, Visual Editing with LLM-based Tool Chaining, an Efficient Distillation Approach for Real-Time Applications. So this is a joint work with Alex, Guy, and Asi from Lightricks, and my advisor, Professor Daphne Shachar from the Hebrew University. Okay, so let's start with the motivation. So our idea is to teach LLMs to use the existing specialized tools in VideoLeap. And what we want to achieve is an AI assistant that democratize all of the advanced capabilities for every user. So right now in VideoLeap, users can use the different tools and play with the parameters, values to satisfy their desired requests. And, you know, as the user is more professional, so it knows better how to play with the tools and the parameters. But we want it will be accessible for all of the users. So our idea is to teach the LLM to use the tools and then satisfies the request of the users. So as a proof of concept, we focus on the tonal color adjustment tasks, which allow users to change video appearance via a textual instruction. So here you can see in the upper row some inputs of users. So input can be an image or a video. And then you can see the stylistic request. And in the second row, you can see the results. So for example, for the Morocco, so you can see that it changed to be with more warm hues, reflecting the Moroccan landscape of desert. And for the matrix, we can see more greenish and black, darker colors, reflecting the characteristics of the matrix movie. Cold tone, for example, more blue colors for the temperature. Okay, so the task is to alter the image or video by adjusting the tonal colors. And let's see an example of some prompts. So here I'm in a VideoLeap, and I'm choosing the asset to be an image of our team from a winery. And first I want to change it to golden hour. Okay, so I expect more yellow and gold tone colors. Okay, now I can write a dark atmosphere, so I will expect more black and darker colors of the image. And last example, you can also put your emoji. So for example, emoji of like freezing, so you expect more blue colors to emphasize the cold weather. And then you can export the project. Okay, so what are the main challenges for our LLM? So first of all, the LLM needs to interpret the user stylistic request, which is specified in natural language. And some of the requests can be vague or require specific knowledge. For example, in the matrix request, so the LLM should be familiar with the matrix movie and its characteristics of green and darker colors. Or for the Morocco request, so the model needs to know that the weather that we are probably mean for the warm weather and the desert of the Moroccan country. Okay, so after understanding the request, then the LLM needs to know which tools to use in the app, because it's not that for every request we need all of the tools, only the relevant tools. And lastly, how to change the parameter values to satisfy this request. So here is a bit more formally, but let's skip it. Okay, so now let's dive deeper into specifically VideoLeap. So we talked about the general case, but now in VideoLeap, we have three tools for the color adjustment task. We have the adjust, which is responsible for the global color grading. We have the selective adjust for color grading for specific colors. And we have filters, which are filters from the VideoLeap app. So here the model needs to choose the correct filter name with intensity. Okay, so now what I want to show you, how the parameters of the tools are changed in the app when we are calling the golden hour. So we can see here, yeah, it works, yeah. So we can see here the list of filters, and then it chooses the faded eye noon. We can see the selective adjust with saturation and luminance that change. And we also can see the parameters of the adjust tool. So for example, saturation is a positive value of 15. So these are the adaptations for the golden hour request. Okay, so actually the project started with the proof of concept led by Alex Cassin, which shows that with the GPT-4, with the zero-shot prompt, we can achieve pretty cool results. So how it works, so we have the user request that goes into VideoLeap, and then we call 3 different prompts, each for the different tools. And then this calls returns a JSON with the parameter values. And if the LLM chooses not to use the tool, it returns empty JSON. And then all of these JSON configurations go back to VideoLeap, which can call the tools with this configuration and apply the changes. Okay, and then I joined the project and I start with prompt engineering. So as a reminder from last lecture, I always recommend you to start with prompt engineering because it's easier to get started with. You can have a lot of improvement only with prompt engineering. And it also gives you some intuition and sense how your current LLM capabilities. So it's recommended to start with prompt engineering before you're going to more expensive solution like fine-tuning. So first of all, I moved the GPT-4 from zero shot to one shot. So I used the idea of in-context learning, the few shot, and specifically in one shot. This allows me to have shorter prompts with shorter responses. So I saved like tokens, and this reduced the cost and the latency. In total, like saving of 50% of tokens and response time. And also important is the validity of the JSON output. So if you use like few shot, so the model has a chance to see one example of the JSON format. So now with the one shot, we have 100% of validity of the output JSON format where we have in zero shot. So GPT-4 had like 15% mistakes in the JSON format. So a cool best practice here is if you use like few shot, it can contribute to better consistent responses. Okay, and then I moved to check GPT 3.5 Turbo, which is a smaller model and much cheaper. Okay, because we want to see if we can achieve reasonable performance with the smaller models. Of course, it's better. But unfortunately, with the zero shot, with the same zero shot prompt as GPT-4, it does not produce the response with the correct JSON format at all. But then after some changes in the prompt, so successfully it produced the correct JSON format, but with totally wrong parameters values. So I moved to the one shot, and then it's produced the correct JSON format, but also looks like the parameters are okay right now. So the interesting question is, how can we, so the interesting question is, does GPT 3.5 Turbo can replace the GPT-4 in a zero shot? And the advantages is that it's 20 times cheaper, 2 times faster, and if it shows reasonable performance, so let's check it. So before I'm going to show you how we compare these models, I want to show you the prompt. So here's the one-shot prompt that I told you. It's with the chain of thought, and this is specifically for the adjust tool. So you are a professional image and video editor. Your goal is to make the color adjust filters based on the user request, and then the standard tools that you can use. So here I detailed the available tools. And then I ask it, suggest how to use these tools to achieve the requested look. So this is like the chain of thought part. And the tools should be combined and worked well together. Write in tool whether you should use the color grading tool, and if yes, suggest how. So in the tool, it will write the reasoning. And then I detailed the available parameters with the ranges of values. And if you decide to use this tool, write in JSON only the parameters that are available, otherwise write empty JSON. So you can see here the inputs is a user request, and the outputs is the tool with the reasoning why to use this tool and with what parameters. And the JSON is actually the values of the parameters that VideoLeap needs in order to apply this request. So here we can see the one-shot example. So I used the golden hour with the user request of a golden hour filter look. And in the outputs, you can see in tool the reasoning. So yes, the global color grading tool should be used. The temperature should be increased to add warm golden tone to the image. Okay, so this is one of the changes that needs to be applied for the golden hour. And you can see it's aligned with the JSON parameters. So you can see temperature is 30. Okay, so the reasoning says to increase the temperature, and also we can see in the actual JSON that we have a positive value for the temperature. And this is one-shot example that I made, of course. It's not the output of the model. This is the one-shot example. And of course, I used the GPT-4 in zero-shot to help me to produce one correct example. This is for the selective adjust, so the same, but for the selective adjust. And then for the filter. So for the filter, we have like a list of available LUT preset filters in VideoLeap. So in the beginning, I detailed the available filters. Then again, suggest how to use this to achieve the requested look. And here, if it does not want to use the tool, there is a filter none, which is the default, which means it will not change the filter. And here the example is with the welding mask filter look. So welding mask is a מסכת ריתוך. And in this example, we expect like a dark and green color of מסכת ריתוך, using the מסכת ריתוך. So actually there is a filter which is suitable, which is the night vision. Okay, so this is the one-shot example. Okay, now let's talk about how we compared GPT 3.5 in one-shot to GPT-4 in zero-shot, the baseline. So of course, going directly to an online A/B test is costly and takes time. So I had to find some way to convince the product team that is worth to consider A/B test. So what I did is a blind experiment in which I gave some participants questions with user request, and then the outputs of the two different models. So one of them will be the GPT 3.5 one-shot, and one of them the GPT-4 zero-shot. And of course, I didn't tell them which one is which model. This is all of the point. And the participant should choose which model produce a better response, which is more relevant and looks good. And also, they can be neutral if there is no big difference or they don't know the answer. Okay, so here we can see, here we can see different prompts. For example, this emoji, neon, shadow depth, cold tone. So for example, here I would say neutral because the results are pretty the same. Charlie Chaplin, the welding mask. And totally the result is that Charlie Chaplin and cold tone, so it's neutral. For dark atmosphere, most people think model A is better. For neon, model B. And then for shadow depth and X-ray, model A. And for the emoji, model B. So what we can see, there is no one clear victory for a model. There is no one model that's definitely better than the other. And I can tell you right now that A actually was the GPT 3.5 one-shot. So that was enough to convince them that we can move forward for an online A/B test. So we had the A/B test like for 1 month. And then all of us, and then in this phase, actually the management of Lightricks told us that with GPT-4, it will be a problem to go into production because it's costly and we don't know how many users and requests we will get. So all of us actually hope that the GPT 3.5 Turbo will deliver comparable results and we can move on with this project. And what we got, so you can see here, the percentage of projects that used with each feature. So the percentage of a project that used each feature were exported. So the measurement here is export the project with the feature. Here we have different features from VideoLeap. And the rightmost is the AI recallout. So this is our feature. And you can see here that variant 1 is 35.6%, which is more than variant 2, 31.2. So not only comparable results, but actually GPT 3.5 one-shot is the winner for this experiment. And our conjecture is that it's not only about the performance and the quality of the image, it's also about the overall experience. And I remind you that this is a smaller model. That's why you have better latency. So the overall experience of the users can be better, which influence the result. But we don't care. We want a better model, of course. So we concluded with the GPT 3.5 Turbo. And then we ask, can we do better? So what are the current drawbacks of this solution? So first of all, we have a dependency on a model which is closed model of OpenAI. And this model also has usage costs. So I know it's not expensive like GPT-4, but still we need to pay for this model. And if we will grow and have more users and requests, so it will be more and more. And I think mainly we are dependent on another company. They can shut down the model, make it deprecated, change the version. So this is one disadvantage. In addition, large language models like GPT 3.5 Turbo, so it's a model with more than 100 billion parameters. So usually for this model, the latency will be high. So it's not suitable for like real-time applications. So when I mean high, it can be like seconds, 5 seconds. But if you want like response like in seconds or less, so it's better that you have a smaller model. And lastly, so we have no integration of user preferences. And if you remember, I told you that Alex produced results, but we think the results are cool, but we don't know actually the taste of the users. And what we believe is that the correct way is that the user will determine what is a good response. So right now we have GPT-3 that with these responses, as it's a prompting, so there is no training on some users' preferences, so we don't know if every response is actually good. Okay, so this is our proposed solution. So we propose a distillation framework, fine-tuning a smaller student LLM with guidance of the larger teacher LLM and user behavioral signals. Okay, so distillation in general is when we create data by using the responses of a larger model, the teacher. So we collect data of the responses of the teacher to request of the users in production. And then we can use this data to fine-tune a smaller model to mimic the behavior of the larger model, okay? But we also can take advantage of the user behavioral signals and maybe achieve not only comparable results, but even better. So our proposed solution advantages is that we will use a smaller model which is open source and free. And smaller LLMs have better latency, so we can improve the latency a lot. And finally, fine-tuning on high-quality data that better align with user preferences. So we give the user preferences into account. Okay, so now let's dive deeper into our approach, the distillation approach. Okay, so this is like an overview. So in the first phase, we have the data collection. So I remind you, we concluded the experiment with GPT 3.5 Turbo. So we collect for 4 months user requests with the teacher LLM responses and also feedback information from the users, whether they export the result per tool. Okay, so we have this. We can use this to filter the data to have it more high quality data. I will show you later. And then we have data processing for fine-tuning, where we take this data and inject it into prompts for fine-tuning. Then we random split the data for training and test set, and we fine-tune a student LLM on the training. Then our next component is the offline evaluation. So we don't want to, so online A/B test again is expensive, it takes time, and we would like to develop offline metrics that will predict how the student LLM will perform in an online A/B test. So this is the offline evaluation. We take into account the tool selection and parameters prediction evaluation. Okay, and then we use an efficient data augmentation technique. So usually in fine-tuning, you have the problem of lack of training data. It's called like the low data regime, that you don't have enough data for training. So data augmentation is the technique to add another data, which is make a lot of impact. So what we are doing here, so we evaluate the performance in offline, and we take only the mistakes from the training. And what we want to do is to create similar requests to these mistakes and enrich the training with this request. So what we are doing is we're extending the training set with similar samples which are similar to the weak data points. So it's very efficient to add this data. Okay, so lastly, we have the online evaluation when we are getting the two student LLMs. So here we actually determine which model is better. But we will go here only when we have like a recommendation from the offline evaluation. Okay, so let's start with the data collection, the first step. So our teacher LLM, again, GPT 3.5 Turbo. So we serve the users for 4 months. This is the data collection period before fine-tuning. Okay, data as the user intent, for example, X-ray, and then the output of the teacher, which tools to use and which parameters values, and also information whether the user exports this result per tool. And then we have data filtering. So here is how I ensure I have very high quality data. So first of all, let's filter out if you have 0 export for a request. So for some prompt, if there is no engagement, so I don't want to take it into our training. And in addition, what we have is that actually for the same request, our teacher LLM can output different solutions. So for example, take golden hour, which is a very popular request also for different users. So the teacher LLM can produce several different solutions for golden hour. And now we have the chance to take only the one solution which maximizes the export rate. Okay, so this is the way how I create data which is aligned to the total aggregated taste of the user. So it's not personalization for specific user, but aggregated for all of the user. Yeah, question. So I want to, okay, so the question is it important for the model to know which sample? So what I want to do here is to create very high quality data with only samples that I know that the response produce like very good results. So what you're talking is maybe a different approach. You can train on positive and negative examples, but here I'm doing like very straightforward supervised fine-tuning. So I prefer my data to be, so my data is positive examples and I prefer to have the best possible examples. Okay, cool. So the prompts I show you, it's like the one-shot prompt with chain of thought that I showed before. So in total, we have more than 9,000 user intents in our data, each with corresponding teacher outputs. So in total, actually, it's like 27 and more rows of data. Then we process this data for fine-tuning. So here is another best practice. So now the prompts for fine-tuning are much more concise. Because think about it, the model is going to see thousands of examples. So you don't need to give him like the large prompt from the teacher. Now for fine-tuning, you can have more shorter prompt because the model we're going to see a lot of examples. And this is also another best practice. And also if you use a smaller model, so it's recommended you will not give it like a very long prompt. It's not like GPT, okay? Another factor is that we decided to omit the rationale. So as I explained you, there is the chain of thought part where it in free text explain why to use the tool and what are the changes, and then the actual parameters values. So since we are prioritize low latency with our student LLM, so we omitted the rationale. Another design choice is that our student LLM is trained on all of the 3 tools. So in the training, I give it examples for adjust, for selective adjust, for filter. So this is like a multitask instruction. So we have one unified model that can predict for all of the tools, okay? Otherwise, we need like 3 fine-tuned models for every tool and it's not scalable. And okay, so this is just the prompt for the filter tool for fine-tuning. So you can see it's much shorter. So let's see. So this is for Llama 2. So we start with the inst format and then a list of the LUT preset. And then the user request is injected. And a very short description of the parameters of the JSON, the intensity. And then I ask it just write the parameters with the name and intensity attributes. So this is a much shorter prompt. Okay, lastly is the data splitting. So we want to split the data into training set and test set. So I'm taking here for test set 1,000 unique user intents. So each with the teacher output. So we have 3,000 samples in tests. And then the remaining go to training. And each row includes the user intent and the 3 tool outputs. Okay? So what we can see here is that we have, for every tool, we have 1,000 in the test and 8,252 in training. And a cool statistics here is how many times the teacher LLM choose to use the tool. So as you remember, I told you that it's not always the case that you need to use the tool. So we can see here, for example, for adjust, if we look at the test row, that 91% of the cases, the model choose to use the adjust tool, and 35 of the cases to use the selective adjust tool, and 68 for the cases of the filter. So we can see the adjust tool is very useful almost in every request. And for example, the selective adjust, most of the time you don't need to use the tool, according to the teacher. Okay, then we have the phase of supervised fine-tuning. So now we want to fine-tune the student LLM with the data, the high-quality data that we collected. So data is pairs of X and Y. So X is the prompt, including the instruction and the user intent, and Y is the completion of the teacher LLM. So here we consider 2 families of models. So first family is, so I'm talking about models for the student. So first family is the autoregressive model, also called decoder only. Here we take the Llama 2 7 billion chat, which is actually the same model that I showed you in the previous session. So in this model, we want to maximize the autoregressive objective, which is maximize the log probability of the target word, YT, given prior words Y1 to YT-1, and model parameters theta. In addition, we take sequence to sequence, also called encoder-decoder models. So here you have the T5 model of Google, which is a model for sequence to sequence. And actually, Flan T5, for those of you that don't know, it's just a fine-tuned version of T5 that supports instruction. So it shows much better performance when you give prompt with instruction. And actually, Flan T5 is like a suite of models from 80 million parameters, which is very small, until 11 billion parameters, which is the Flan T5 extra large, which is more than the Llama 2 7 billion. So my motivation here is to check whether I can achieve a comparable performance with even smaller model, okay? So we have the teacher, which is like a billion of parameters. Llama 2, if we will fine-tune it, it's 7 billion. And now I take Flan T5 base with 250 million parameters. Okay, so the next component is the offline evaluation metrics. And again, the motivation, we want to evaluate the student LLM on our test set in order to know its performance before we are going to the A/B test. So here we develop metrics that we want to measure that takes the 2 aspects of the task. So first, the tool selection. So this is for the model's ability to decide correctly whether to use a tool, okay? And we measure precision and recall, and we report the tool selection score to be the F1 score. Okay, whether the model know if it needs to choose the tool or not. And the second one is the quality. So given that you choose the tool, how well you predicted the parameters for the tool. So for the filter tool, it's easy. We can measure the accuracy. So you have like the ground truth filter class and the predicted of the model, and you compare with exact match. Very easy. And for adjust and selective adjust, so here we treat the JSON of parameters of integers values as a vector of parameters. And then we can compute the cosine similarity between the predicted parameters of the model to the ground truth vector of parameters. And what we are doing, we calculate the mean cosine similarity across all of the samples. But I want you to note that this metric is overly strict because we are assuming that there is one correct answer, but I told you that it's not the case. So we are comparing to a specific ground truth answer, even though there can be other combination of parameters which perform good. The final score is the harmonic mean between tool selection score and quality score. So we want to emphasize high performance in both. And lastly, we have the overall score, which is just the average of the final scores of the tools. Okay, so after we develop the metrics, we want to have also a reality check on our offline metrics. So in our metrics is for the configuration of the JSON parameters. But we want also to see in our eyes what are the produced videos and images if you apply these parameters. So this is like the offline evaluation reality check on the images. So how we do it, we take the produced parameters and apply the results in our VideoLeap app to get the results. And here we analyze like a random sample with human annotators per sample. So we have like 3 annotators per sample. But we also discussed like automatic evaluation if you're interested. So maybe it's for future work, but in our paper, actually we use human, but if we want to automatically evaluate the image. So some cool metrics you should be familiar with. So the static score is a metric that predicts people ratings between 1 and 10 for how well the image look, which can be relevant. And then we have the peak score, which evaluates the relevancy based on a preference model that was trained on text-to-image prompts. So this is the peak score give you a score how well the image is aligned with the text according to what humans will say. Okay, so this can also be relevant to us. But then GPT-4 Vision is released in this time of this research. So now I'll show you how can we use GPT-4 Vision to determine which is better. So here you can see we have the 3 images. So the A is the source image, the input asset, and then B and C, 2 outputs of different models. 2, for example, student models, and we want to determine for the Morocco intent, which result is better. So of course, it's just an easy example for, just for example, C is the answer. We can see we have more warm hues, and B is just the opposite. It's more even maybe London. So the prompt again with the chain of thought, I said, please describe the transformation first. So what's the transformation to move from B and C from A? And then after describe the transformation, choose the correct answer. So in the first paragraph, we have the description of every image and the transformation that was made. And then we have that the Morocco filter look is typically characterized by warm tones with emphasis on orange, reds, and earthy colors that reflects the landscapes and architecture of Morocco. So here the model explain what you think the Morocco request is. And then the final answer, C, better represents the Morocco filter look due to its warm and vibrant color palette. Okay, so here is just example how we can use GPT-4 Vision if we want like automatically to determine which result is better. Yes, okay, so any questions so far? Okay. Okay, so let's talk about the data augmentation that I told you. So we are inspired by another research by Lee et al. And what we are doing, we iteratively run offline evaluation on the training set. And in this iterative algorithm, the first component is to identify the student LLM predictions that are mistake, okay? So this is when the student is different from the ground truth. So for the filter, again, it's easy to check if you have a mistake, if your predicted filter class is different from the ground truth. And for the adjust and selective adjust, so we define a mistake to be when the cosine similarity of specific sample is lower than the average if no augmentation was made. And the second part is taking all of the mistakes and use another LLM to generate similar samples. Okay, so here, for example, if we have a mistake call on the prompt cool tone, we want to create a similar request, for example, cool morning. And then we take this request with the original teacher LLM response and adding it to the training set. Okay, we augment an intent when we have a mistake in at least one of the tools. And here is the prompt to generate the additional request, which is similar. So we are requesting for a similar user request, which is different from the input, but share many similar characteristics. So here is a few shot prompt. You can see in these examples that we have cool morning, and then a similar is cool tone. So semantically, it's not the same, but similar concept. And dark atmosphere, dark night, and vintage film, retro cinema. Okay, so this was the few shot prompt for our GPT-4 model to generate a similar request. Okay, and last thing is the online evaluation. So here is the A/B test. Our metric is the project completion rate. So we calculate number of projects exported out of number of projects used. And for us, this metric is the indication of satisfaction of the user and the overall experience. So yeah. Now let's see some results, okay? So this was all of our approach. Now our research questions. So we first ask, how do student LLMs perform, and do they effectively mimic the teacher? Okay, so we propose here smaller models. Let's see how well they perform according to our metrics. And the second question is augmentation effective in low data regimes? So we are specifically interested in the case of low data regimes. So for our experiments, our models are, again, the teacher GPT 3.5 Turbo, and the students, we have the Llama 2 7 billion chat with LoRa and quantization. This run on A100 GPU of NVIDIA. And we have Flanty5 base, the smaller LLM, which is faster, and also runs on L4 GPU, which is 5 times cheaper. And we train both of the models for 10 epochs and selecting the best checkpoint from the last 3 epochs. And the metric is the overall score, the final average of the tools. Okay, so we don't take the result in the last epoch, we take the maximum over the last 3. And here we can see the results. So we have in parentheses the metrics. So the leftmost number is for the tool selection score, the middle number is for the quality, and the rightmost number in the parentheses is the final score. And on the rightmost column, we have the overall score, which is the average of the final score. So let's have an example. In row 1, we have that the final score for adjust is 76, final score for selective is 70, and for filter 76. So the overall will be the average, which is 74. And what we can see here is that actually Llama 2 7 billion and Flanty5 base have very similar performance. If we look at row 1, so this is for Llama, it's 74, and if we look at row 4, we have the overall score of 72. So it's not a big gap. And interestingly, we also evaluate subset of the test set. Okay, so we want to check what happened for more popular requests. So we denote by RI is intense with at least I calls. Okay, so R3, for examples, is intense with at least 3 calls. So what we found for both of the models, that R5 has better performance than R3, which has better performance than all of the test set. So this means that for more popular requests, the performance are even better. And this is important for production because more popular requests cover more of the traffic. Okay, and the latency data. So the overall latency for the tools, we have 1.63 seconds for Llama 2 on the A100 NVIDIA GPU, and 1.38 for Flanty5 on the L4 GPU. And this latency is much lower than the teacher LLM, which was the GPT 3.5, which has between 3 to 4 seconds, which is lower than the GPT-4, which has 9 to 10 seconds. So you can see the improvement in latency. And now for the reality check that I told you. So we sampled 15 generated images and used 3 calibrated team annotators to review the samples. And we report the majority vote of the annotators. And we ask the annotators 2 criteria. Is the image relevant to the intent? And does the model correctly mimic the teacher? So here we can see in the first row, we have the Morocco. So I think all annotators said in this example, which is easy, that all of the results are relevant to the intent, also the teacher, also the students, and also the students correctly mimic the teacher. But in the second example, which is more complex, you can see, so I think it was controversial, maybe the majority say that the results are relevant, but we can see here that the students, they don't correctly mimic the teacher. Maybe this is relevant responses, but they don't correctly mimic the teacher. And also both of the students are different from each other, okay? So we aggregated all of these results to these questions, and we got that in terms of relevancy, so between 13 and 14 out of 15 of the models, annotators say the response is relevant, which means that also the teacher and also the students, quite relevant results. And in the question of whether the student LLM correctly mimic the teacher, so we got in both of the models 11 out of 15. Okay, not necessarily on the same samples, but in total 11, which means that we have like very comparable models. And this is aligned with our offline metrics that you saw, like the small gap between 74 and 72. And this is for reality check. So we got relevant results, which is cool. And also we got the comparable performance students. Okay, now we have I will tell you about the A/B test that we've done. So again, project completion rate for user satisfaction, this is the metric. So our first A/B test experiment was with the teacher LLM that we collected data for 4 months with the Llama 2 7 billion, the student. And we got that the completion rate of the teacher was 96% out of the Llama 2. So Llama 2 is a bit better, but not statistically significant. But of course, for us, it's like comparable performance, and we can conclude the experiment with Llama 2, which has better latency and costs. So here we achieved our first open source model for this task. And then we said, okay, maybe let's improve it more and evaluate in another A/B test Llama 2 and Flanty5 base, which is smaller. And we got that Flanty5 has 99% out of Llama. So Llama 2 again, but is a bit better, not statistically significant. And we, of course, prefer to take the Flanty5, which has much better latency and cost. And what we can see here is also that these metrics from the online A/B test correctly predicted from the offline, which says that the performance will be very similar. And then we go to the A/B test and we will see it. Okay, now for the augmentation. So what we did, we evaluated the augmentation on different sizes of the training using random sampling. And then we had mistakes on the random sample of 1,000. So we have a fixed number of random sample when we are looking for mistakes. So no matter how much bigger the training size, you're evaluated on 1,000. So the augmentation will be very similar between the subsets. Okay, GPT-4 was used to generate the similar request, and here is the results. So we can see that for all of the training size with 8,252, we got overall score. This is for Flanty5 base. We got the 0.72. Without augmentation, if we take 1/8 of the training, so this is like 1,031. So we got 0.52, okay? But if we use the augmentation on 8 of the samples, we improved by 13, okay? Which is 25% improvement, and this is only with one iteration of the augmentation technique. So we can see that our augmentation is very effective. I show you here the 8%, but in the paper you can see like the different subset percentage. Okay, so I think we have like 15 minutes. So now what we have seen, so now I will talk about like conclusion, what we have seen, and ideas for future work. So if you want to have more work, so we have a lot of ideas. Okay, so what we have seen, we introduce a novel NLP application for automatic editing using LLMs. And we focus specifically on the tonal color adjustment. And in our approach, we fine-tune a smaller student LLM with guidance of larger teacher LLM, but we also leverage the user behavioral signals. And in our approach, we propose the offline evaluation metrics and show that the student models succeeded in matching the performance of the teacher in both offline and online experiments. And our solution finally is a significantly reduced cost and latency, which is crucial for real-time industry applications and makes this project like very efficient. And now for a few ideas for future work. So first of all, you remember that I talked about the rationale, the reasoning part that I omitted from the student because I want a better latency. So actually, there is another paper from Google that shows that if you add this reasoning together with the predicted parameters and train it with multitask framework, so the loss will be divided into 2 parts, the reasoning and the actual parameters that you predict, so you can improve the results. So it will be interesting to validate it. Second, to quantify the benefits of using our user signals rather than just use all of the outputs of GPT. So maybe we need another research question to check how much the user's data helps us. And also consider another methods for user feedback. So in our approach, we have like user feedback, which is global for all of the users, but maybe we can work with personalization. So we will give response which is specified for this user taste. Next thing is to teach the LLM to take dependencies into account. So right now, it's a naive approach of taking first call to adjust, then call to selective adjust, and then to filter. And the LLM doesn't know in the other prompts what was the result. So maybe to teach it to take dependencies into account will improve the flexibility. And we want also to extend the research. So in our implementation, it's one-up response. So you write, for example, golden hour, and you get the response. But think that we can make a conversational agent, okay? And last point, we can apply this research into additional tools, features, and applications. So for example, we have the transition between clips or light effects, so other features in VideoLeap, and also features in Facetune. So this approach is like a general approach. Okay, so that's it. Thanks for listening, and I think we have like few minutes for questions. Yes. Yeah, so in this task, it was 3 tools, but we can, it's scalable for if it was like 4 or 5 tools. So the best practices in this approach can be implemented in different number of tools. Another question? Okay. Okay, thank you for listening.
Thank you for sharing 2 sessions. It was a lot of work, and I'm happy that we split it to 2 different sessions. There's not a lot of people here, but I think it's really important for who it is relevant for. So we knew it is a very specific thing that not everyone needs to learn, but who needs it, it's very meaningful. So thank you all, and I'm sending the feedback form. We'll really like you to answer it also at Zoom. Thank you.